Morning, everyone. Let's get started. So first of all, we have released the homework 3, and this time is mainly about implementation of perceptron. This is pretty straightforward. We got 2 weeks to finish that. I think that's more than enough. But again, please start early, like today or tomorrow, so that you can have a sufficient time, and also you can better leverage our office hour. And second thing is just reminder about our midterm project report will be due on this Friday. Please follow the instructions in our course webpage. You don't need to write very long report. You just need to cover the points we want to see, which are described in our course webpage. That should be fine. Don't worry that your current model or algorithm seems not working well. That's totally fine. As long as you can cover what we want to see in your report, usually you get full grade. Okay. So let us just give a quick review about what we have discussed last week, right? So we went back to the computational learning theory. We'll talk about a more general, more realistic setting, which we call the agnostic learning, right? Agnostic learning means that your target function could be outside of the hypothesis space, right? So the hypothesis space is the range of functions your learning algorithm is gonna search over, right? And you try to search some function in your hypothesis space to best fit to the training data, or optimize the loss function, right? And however, if your target function does not stay inside your hypothesis space, that means your training error will not guarantee to be 0. So this is different from what we have previously discussed about computational learning theory. Remember, we assume that, okay, you can always find a hypothesis with 0 training error. Then we talk about sample complexity bound and so on, right? But in practice, we cannot make such a strong assumption. Agnostic learning, of course, is much more realistic. In that case, we can still use some tail bounds. Here, the tail bounds we use is called Hopkins inequality, right? To derive something about the generalization error in terms of the training error, right? So I'm not gonna go through the details, just to give you some sense, just to let everyone recall what we have discussed, right? So, so error S is the training error, right? Error D is the generalization error, right? So we can directly apply the Hopkins inequality to show that with the probability that there exists a single, the probability that a single or a particular hypothesis H, whose true error is more than epsilon away from the training error, is bounded by this exponential factor, right? So the exponential factor is determined by the number of samples and also the distance, the epsilon, right? So you can see that if we increase number of samples for training or increase distance, this probability bound decreases very, very fast, right? Decreases exponentially, right? And to apply more general results, that means we want our conclusion applies to any learning algorithm. That means we don't know which particular hypothesis any algorithm is gonna find, right? So we're gonna change this bound into an existence statement, meaning that what we like to say, okay, how about the probability bound for that there exists a hypothesis whose true error epsilon away from the training error. Right? So this bound can be derived by the so-called union bound. Right? Their first homework, we have reviewed this union bound, and we can easily show that. Okay, for any learning algorithm, if you find a hypothesis whose true error is epsilon away from the training error, this event, the probability, is upper bounded by the size of hypothesis H hypothesis space H times this exponential factor. Right? And then given this probabilistic bound, we would like to say, okay, if I want to control this bound to be as small as possible, that means I want my true error to be not far away from the training error. Right? I want my training error to be small, right? Because I can imagine that after running any learning algorithm, my training error could be relatively small, right? It's not guaranteed to be 0, but it could be quite small, say 5% error, right? But I want my true error to be close to the training error, right? I don't want my training error to be just 5%, but true error is 20%. That's not something I want to happen, right? So, but this is a probabilistic event. Why? Because the training depends on the training data, right? The data itself is random. So there must exist some probability that, okay, your true error is quite bigger than the training error. And we have some bound. That's a good thing, right? We have some bound to characterize this probability. Right? Yeah, let's just think for 5 minutes to digest this information, right? What does this bound deliver? So even in an agnostic learning setting, let me re-emphasize the motivation here, right? Even in an agnostic learning setting, right, we no longer guarantee 0 training error, but we believe that our algorithm can still give me a good small training error, right? Say 5%. Right? And then my hope is that, okay, my generalization error will not be too far away from the training error. See, 5% is the training error, then maybe generalization error is just 6%. That's totally acceptable, right? I don't want the generalization error increase to 20%, while my training error are only 5%. Right? This is not very good, right? But due to the randomness of the training data, remember, a training data will guide your search procedure to find a hypothesis. That's search procedure. Right? Different training data will possibly return you different hypotheses. Right? So that means your learned hypothesis is actually dependent on training data. So there's always, and the training data is random. So there's always a chance that, okay, your true error after learning from some random collected training data is much bigger than the training error. Okay. But good thing is that we know, according to the Hopf stability, we have derived a bound for this probability. Right? This probability, this bound characterizes at most how large my true error will be epsilon away from the training error. Right? And then, since we have a bound, then we can control this probability, right? I want this probability to be smaller than some threshold, say delta, right? So you can see the point, right? Okay. This is a bad event, right? I don't want my true error is too far away from the training error, right? But this is a random event. This is not deterministic. Right? This is possible. And then I cannot completely avoid this to happen. But the good thing is that I know what is the bound of this event to happen. Right? And then I can control the bound so that I can control this event, the chance of this event. Does it make sense? Okay. Let me know if you have any question. Because the mathematical derivation here is not important. We won't ask you to memorize how to prove this. But everyone needs to understand what's the meaning of doing this. And then suppose I want to control the probability that your true error is epsilon away from the training error. This probability to be less than some given delta, right? What we can do is we just solve this bound to be less than, upper bound to be less than even to than delta, right? Then you can solve it in terms of the number of training examples n, right? So then it gives us that, okay, if the number of training example is bigger than this guy, then your probability you got bad generalization error. By bad means, okay, it is too far away from the training error. This chance will be less than delta. Okay. That's the key idea. This is the same idea as same meaning as we discussed for the consistent learning case where you have zero training error. Right? We have zero training error. So we have seen that this bound, the sample complexity bound for the agnostic learning, also reflects the Occam's razors principle, right? Because we can see that if you set the same delta, set the same distance epsilon, right? The larger your hypothesis space, meaning that more complex your model, the more training examples you would like to use to control that the chance of that bad event to be less than delta, right? And meanwhile, if we can switch epsilon and m, so epsilon is actually the difference between the generalization error and the training error, we can obtain the so-called generalization error bound, right? So generalization error bound means that, okay, for any training examples, right, with probability at least 1 minus delta, the difference between the generalization error and the training error is upper bounded by this guy. This is called generalization error bound, right? Just keep it in mind because later we'll see a different bound, but it reflects the same meaning. And we're motivated by this bound to design large margin classifiers like Sepovic machines. So so far for the consistent learning case and agnostic learning case, like we derive the corresponding sample complexity bounds, right? Both bounds rely on a measurement of the complexity of the hypothesis space, which are just logarithm of size hypothesis space. Right? That brings a new issue that what if your hypothesis space is infinite? Right? If it's infinite, then this logarithm of their size is meaningless at all, right? And then your sample complexity bound and also your generalization error bound will be meaningless as well, right? So if your H size hypothesis logarithm is still infinite, this bound is infinite. It just means, okay, the difference between the generalization error and the training error is less than or equal to infinity, right? That doesn't tell us any useful information, right? So we do need some new measurement of the complexity of hypothesis space, but it must be finite, right? Even your hypothesis space is infinite. Right? So there could be many different measurements, right? So we're going to focus on so-called VC dimension, right? Vapnik-Chervonenkis dimension, right? You can view it as a counterpart to size of H, right? But the VC dimension is finite for many, many infinite hypothesis spaces. Okay. So yeah, I'm gonna skip this motivating examples we discussed in the last lecture, right? So let us start talking or discussing about the definition of VC dimension. Right? We'll start with a concept called shattering. What does shattering mean? Suppose I got 2 points. My data set only includes 2 points, right? So we only consider binary classification problem. So that means if we just assign labels for the 2 points, how many possible labeling schemes for the 2 points? 4, right? Because each point is possibly have 2 labels, right? So 2 points means 2 to the power of 2 is just 4 labels, right? So then we'd like to check the expressivity of linear classifiers. How do we check, right? We'd like to say, okay, for each possible labeling scheme, can we find a linear classifier which correctly classify all the labels? Can we? Yes, right? You can see that this 4 figures represent 4 labeling schemes, right? For each labeling scheme, you're going to find one linear classifier which correctly predict every label, right? In the middle, on the bottom, in the middle, on the top, right? In this case, we claim that our linear functions, this is a family of functions, right? Or hypothesis space, are expressive enough to shatter 2 points. Okay. To summarize, right? For the 2 points, for the case of 2 points, right? There are 4 ways to label 2 points. Right? We only consider binary classification. And it is possible to draw a line that separates positive and negative points in all 4 cases. Therefore, we conclude that our linear hypothesis space is expressive enough to shatter 2 points. Does it make sense? Right. And now let us try to consider a more complicated case, right? What if I gave you 14 points? Can we claim that our linear hypothesis space shatters 14 points here? Can we? Need more information? What kind of information do you need? What? Yeah. So shattering means that I'm gonna try every possible labeling for the 14 points, right? If for every possible labeling, I can find a hypothesis in my hypothesis space that perfectly separate the positive and negative examples, then we'll call, okay, we can shatter this 14 points. So now, can we use linear hypothesis space to shatter these 14 points? Why? Yeah, we can just try, right? If we can find a labeling scheme which cannot be correctly or separate by a linear classifier, then we can say, okay, our linear classifiers cannot shatter these 14 points, right? Okay. So for some simple labeling scheme, yeah, of course we can. For example, for this particular labeling scheme, I can find a linear classifier or line well separate positive and negative examples, right? But what if I kind of mix the labels, right? If I mix these labels, you can definitely, you will definitely fail to find any line which can separate all the blue and red points, right? Right. I mean, you can try all kinds of stuff, right? You'll fail, right? So then now we can claim that because we find a counterexample, right? We find a counterexample by my particular labeling scheme on that counterexample. I cannot find any hypothesis in my linear hypothesis space which can correctly predict every examples, right? Labels are very examples. So then our conclusion is that linear functions are not expressive enough to shatter 14 points, right? Because there is at least a labeling that cannot be separated by them. Okay. Of course, if we can enlarge our hypothesis space, right, including not only linear classifiers, but also some kind of nonlinear classifiers, we might still be able to shatter these 14 points, right? For example, I can draw a curve, right? Aperture curve, which can separate all the positive, all the red points from the blue points. Does it make sense? Okay, great. So now let us give a formal definition of shattering. Right? So what's shattering? Consider a set S of examples. We see S is shattered by a set of functions H. So here H is the so-called hypothesis space. Right? We call S can be shattered by H if for every partition of the examples in S into positive and negative examples, there is a function in H that gives exactly these labels to the examples. Right? So that means, okay, for arbitrary possible labelings for every point in S, I can find, or there exists a hypothesis in your hypothesis space H, which can correctly predict every label. Then we see this whole set S can be shattered by my hypothesis space H. Does it make sense? And intuitively, if your hypothesis H is rich, right? The richer H, the more likely it can shatter a larger set of points, right? Because you have more candidates. Okay, before we go to see more concrete examples, any question regarding the definition here? Yeah, great. So next, we're gonna use a few examples to showcase how do we count shattering, right? Let us look at the first infinite hypothesis space we're going to discuss, which is called half interval, right? Or left bounded intervals. So each classifier in my left bounded interval hypothesis space is described by an interval 0 and A. So left end is 0, right? Right end is A. And A is positive, right? So this classifier, this half left bounded interval classifies all the points inside the interval as positive and outside as negative. So first, we would like to say, can left bounded intervals shatter one point? And it does? It does, right? Right. We just leverage the original definition, right? So think about any point here, Consider shattering means that, okay, I need to enumerate all possible labelings on the set of points, right? So here's the single point, so we only have two possible labels, right? The first label is that it is positive, right? Then I can construct a left bounded interval such that your right end A is bigger than the position of your point, right? So it must classify this point as positive to make correct prediction, right? And there's another possible labeling for this point will be negative, right? In this case, I can choose a hypothesis where your A is less than the location of your point, right? Now, because this point is outside of your interval, so it will be classified as negative. So now we can see that the left bounded interval hypothesis space can shatter one point, right? So let's do 2 points. Can we shatter 2 points by using left bounded intervals? Any thought? The answer is no. Why? Let us try, right? Let us try. If we can find a counter example, like some kind of particular labeling over these 2 points, such that you can construct any left bounded interval to give a correct prediction of the labels on the 2 points, then we can claim you are not good enough or expressive enough to shatter 2 points, right? So here is one labeling, possible labeling, right? So this is the position of 2 points, right? I can assign a negative label on the left point and a positive label on the right point. And let's see if we can find a left bounded interval to correctly classify both examples. Can we do that? No, right? Why no? You just do a little bit of reasoning, we can find the answer, right? So if I put A to be here, I mean to be smaller than the left point, to the left of the left point, then both points are classified as negative, right? So make one mistake, right? If we put it in the middle, what will happen? You just tell me. You're going to classify the left point as positive and right point as negative, right? So both examples are classified wrongly. And what if we put A on the right of the right point? You're saying interval? No, this is our definition, right? That's how we choose the hypothesis space, right? I need to, if you're using my hypothesis space, you need to follow my setting, right? So that's why I asked that, oh, okay, A must be positive. If, in third case, like if you put A even farther away, even on the right of the right point, then both points are classified as negative, right? Oh, sorry, both points classified as positive. And of course, the left point will be wrongly classified. Right? And there are only 2 possible locations, or 3 possible locations for A, right? Here, here, and here. So that means you have enumerate all possible left bounded intervals, but you still fail to correctly classify both points. Therefore, we find a particular labeling such that any left bounded interval fails to predict the labelings. Okay. So that means sets of 2 points cannot be shattered by my left bounded interval hypothesis space. So you can see that even this hypothesis space is huge. Why it's huge? Because it's infinite. It contains infinite many possible classifiers, but this space can only shatter 1 point. The expressivity is highly limited, right? So now let us look at a more flexible hypothesis space, right? So now we do not fix the left end to be 0. We allow the interval, both ends of the interval can be flexibly chosen, A and B. We only require that, okay, B must be bigger than A, because to maintain a valid interval, your right end must be bigger than the left end, right? And then this is my new hypothesis space, right? It consists of sets of intervals on real axis A and B, and A and B can be chosen arbitrarily as long as B is bigger than A. Then let's see how many points can be shattered by my interval hypothesis space. First, it is fairly easy to shatter 1 point, right? I'm not gonna repeat that again, so it's really straightforward to see that, right? So then, giving you 2 arbitrary points, right? Can these 2 points shattered by the interval hypothesis space? Seems right? So we can try that, right? So this is my arbitrary interval classifier A and B. Remember, A and B are both flexible, right? We classify all the points inside the interval as positive, outside as negative, right? So now suppose I'm choosing arbitrary 2 points, right? For all positive labeling or all negative labeling, it's fairly easy to find the corresponding interval A and B to correctly classify both of them, right? Right. For all positive labeling, you can choose A and B large enough to include both points, right? And for all positive, for all negative labeling, you can choose A and B outside of them, right? So now let us look at the third case where left point are labeled as positive and right point are labeled as is labeled as negative, right? How can we correctly classify them with an interval? Where do you gonna put A and B? Yeah, it's fairly easy to find, right? I can just pick up A here and pick up B in between, right? So then I can correctly classify this labeling scheme, right? So the remaining case will be, okay, the left point is labeled as negative and right point is labeled as positive. Then how are we gonna choose a interval classifier? Any thought? Yes, right? So I can just pick up A here and B here, right? So that we can only include this positive labeled data point inside the interval, right? The negative labeled data point is outside interval. So I can still correctly predict the two labels, right? So now we have enumerated all 4 possible labelings over these 2 points. We can find that for every possible labeling, we have a corresponding interval classifier correctly predict the labels, right? So now we find that our interval hypothesis space can shatter 2 points, right? This is an improvement, right? So remember, for left bounded intervals, it cannot shatter 2 points. Now, by allowing the left end of the interval to be flexibly chosen, we can shatter 2 points now. Right? We actually increase the expressivity of our hypothesis space. But again, you can see that this one is also a infinite hypothesis space, right? Left bounded interval hypothesis space is infinite, and intervals space is infinite, right? But there's still a big difference in terms of their expressivity. Right? Any questions so far? Now let's try to consider 3 points, right? Let's see if we can use our interval classifiers to shatter 3 points. Can we do that? To verify this, we need to enumerate all possible labelings over the 3 points. How many possible labelings do we have? Three points. 2 to the 3, right? Because every point you have 2 possible labels, right? So you got 3 points, that means you got 2 to the 3 possible labels, which is 8, right? And I'm not gonna enumerate all 8 labelings and check, right? I just give you a counterexample to show that actually the flexible interval hypothesis space cannot shatter 3 points. Right? Here's the counterexample, right? This is my 3 points. Right? If I pick up a particular labeling where I assign positive labels on the left end and right end, and negative label on the example in the middle, right? You can see that we're not able to find any interval to correctly classify all 3 points. Why? Because if we want to correctly predict the left point and right point, you have to make A and B to be further apart so that it can include both left point and right point, right? That means the point in the middle must also be included in the interval, right? So that means it will be classified as positive. Unfortunately, it is negative, right? It is labeled as negative. So you won't be able to correctly classify all the 3 points, right? Or you can also consider like where I put A and B, you try all possible positions. You'll find that you'll never be able to find an interval which can correctly classify all 3 points here. Does it make sense? Mm-hmm.
In position, you could imagine an example where like 2 points are on top of each other, but one's the plus and one's the minus.
No, that's not the. I mean that case. When we talk about shattering, it is about one particular set of points. It's not like okay, I'm shattering 10 sets of points simultaneously. We're just talking about okay, given a particular 3 points here, can we do that? Right? And of course, you can find one set of points, say if they overlap with each other, it cannot be shattered by any hypothesis space, right? It's fine. But you later will see that as a key component of the definition of VC dimension, we don't require it can shatter any set of points. Only require that, okay, you can find a set of points that can be shattered, then that's fine. Mm-hmm. Another question? Everyone feels straightforward about this, right? It's just enumerating labels and doing some trying, right? Okay, so now we can see that our new hypothesis space, which consists of intervals, right? It can shatter 1 point or 2 points, right? But for sets of 3 points, they cannot be shattered, right? So we can also see the bottleneck of this interval hypothesis space, right? Although it seems more flexible than left bounded interval, it's still quite restricted, right? I can shatter 2 points, but we cannot shatter 3 points. Any 3 points cannot shatter, actually. Then let us try to look at even more flexible hypothesis space, which is called linear classifiers or half spaces. In the plane, we call linear classifiers half spaces. It just means that the classification boundary is going to partition the whole space into 2 half spaces, right? And we'll see that it's very easy to shatter 1 point by half spaces. And 2 points, can 2 points be shattered by half spaces? or linear classifiers? Yes, right? We show that as an example at very beginning, right? And then can we increase number of points to 3 points? And then we need to do some work, right? According to the definition, we have to enumerate all possible labeling schemes over 3 points. That means you got 8 possible labelings, right? And you're going to check for every case, can you find a corresponding linear classifier which correctly predict the labels, right? And it turns out yes. Right? For every case of this, for every possible cases labeling schemes, I can find a corresponding linear classifier which perfectly separate positive and negative examples. Then we can conclude half spaces can shatter 3 points. And then we want to ask, well, can half space shatter 4 points, right? And so on. So 4 points, you have to enumerate 16 possible labelings, right? That's really tedious. But let's just first not to worry about like whether you're able to draw all 16 labeling schemes and find lines, right? It's kind of tedious, right? So, but we can view it in general as an adversarial game, right? For shattering, right? Considering U and adversary, right? You want to claim that your hypothesis class H can shatter this D points. And the adversary says, okay, that's what do you think, right? I'm going to challenge you with my secret labeling scheme, right? I show this to you and it will defeat you, right? And then you just look at your hypothesis library, right? And find one which can predict your evil labeling. If you can do this, you present it to the adversary, say, okay, your labeling is simple for me, right? And the adversary said, oh, you win this round, but I will be back. I'll provide another one, right? Just keep doing it. If the adversary has exhausted all possible labelings, and that means you win, right? If the adversary provides some real evil labeling that you fail to find any classifier in your hypothesis space to correctly predict them, then you lose, right? And you have to admit that, okay, your hypothesis class actually cannot shatter this set of points. Does it make sense? Right. So if for instance space X, right? So remember we'll talk about instance space X. That means X could be infinite as well. If we can see arbitrarily large finite subsets of some instance space X can be shattered by my hypothesis space H, then we claim that our hypothesis space H can shatter infinite points. That's the definition. So we say, when we say hypothesis space H can shatter infinite number of points, it just means you can pick arbitrary large finite subset from that points, and they can be shattered by our hypothesis space. It doesn't really mean like, okay, you really consider labeling over infinite many points and see if you can shatter that or not. It's not, the definition is not like that. And the second intuition is that for a particular instance space X, right, which might in practice correspond to our feature space, right? We can imagine the larger the subset of our feature space X that can be shattered, the more expressive the hypothesis space H is, right? Any questions so far before we give a formal definition of easy dimension? Okay, great. So now we start talking about what is VC dimension. VC dimension is based upon this concept shattering. The VC dimension of a hypothesis space H over instance space X is the size of the largest finite subset of X that can be shattered by H. It reflects 2 points. If there exists any subset of size D that can be shattered, the VC dimension of H will be no less than D. Remember, this is an existent statement. It doesn't require that, okay, every subset of size D must be shattered. As long as you can find one subset of size D that can be shattered, then we claim that the VC dimension is no less than D. Right? Even you can find one, right? And the second point is that if there's no subset of size D that can be shattered, then VC dimension is less than D. Does it make sense? Any questions so far? Right. So you can imagine that if you want to mathematically, not mathematically, just mechanically compute the VC dimension, right? You just search over the subset of instance space, right? You look at, okay, if you can find just one subset, say of size 1, if it can be shattered by my hypothesis space, then I can claim that my VC dimension is at least 1, right? And then I increase the number of points in the instance space to be 2, right? If I can find one particular 2 points in my instance space that can be shattered by my H, then we claim that this dimension is at least 2, right? You just keep doing this until you find that for any, say, suppose you have arrived at D, right? So you have already found a subset of size D that can be shattered by H, then I claim that this dimension is at least D, right? And then you increase to D plus 1. And this time you find out, okay, any subset of size D cannot be shattered by my hypothesis space. Then you should stop. Because your VC dimension will be less than D plus 1, and that gives you the conclusion your VC dimension will be just D. Does it make sense? Any question? Everyone feels comfortable? Okay. So here we list a set of VC dimensions for some commonly used classifiers to give you a sense about the flexibility or expressivity of different machine learning models, right? So for the half intervals, the VC dimension is simply 1. That is left bounded intervals, right? Because as we have already tried, right? It can shatter 1 point, but it cannot shatter any 2 points. So its VC dimension is 1, right? For interval classifiers, meaning both left ends and right ends are flexible, then the VC dimension is 2, right? That means you can find 2 points, just one subset of 2 points, right? As you just mentioned, right? What if they overlap? That's fine. That's a failure case. But as long as you can find a successful case, that's fine, right? And then our VC dimension is at least 2. But if you increase the number of points to be 3, you can find that for any position of 3 points, you cannot shatter them by intervals. Then our VC dimension is 2. And half spaces in the plane, that means just linear classifiers in the plane, right? The VC dimension is 3. That means for any 4 points, you cannot shatter them by linear classifiers. This is our homework problem. Think about that. It's a little bit tedious to solve that problem, but it's a very good way to deepen our understanding of this concept. And in general, for linear classifiers in D dimension, the VC dimension is D plus 1. Okay. Of course, showing this is not relying on you enumerate all possible to the power of D labelings, right? They have some other ways to do that, but good thing is that we don't need to do that, right? We just need to keep it in our mind. The VC dimension for general linear classifiers in D dimensions is D plus 1. And for neural networks, the VC dimension is number of parameters. So you can see the larger the neural network, the more complicated the neural network, actually, the more expressive, right? And for one nearest neighbors, the VC dimension is infinite. So that means one nearest neighbor looks like very simple classifiers, but it has biggest expressivity. But anyway, all those results have shown that have demonstrated or verified by our intuition, right? A rich set of functions shatter a larger set of points. Right? Okay. So now let us go back to see why we should introduce VC dimension. Because it relates to the sample complexity. Previously, we discussed about consistent learners, meaning that you guarantee to have a zero training error, and agnostic learning where you don't have a zero training error guarantee, right? In both cases, we can derive that the sample complexity depends on the log of size of hypothesis space, right? Which won't be useful when your hypothesis space is infinite. And unfortunately, in practice, we often choose infinite hypothesis space, right? That's why we should use some other measurement for the complexity of your hypothesis space. That is what motivates the so-called VC dimension. Then there's a question, right? If you use VC dimension as a measure of the expressivity, right, what will be the sample complexity bound? What will be the generalization error bound? Right? And we're not going through the proof here, right, or math details here, because it actually belongs to some particular computational learning theory class. Is out of our scope, right? Here we just list the result, right? So given a training set D with M examples, if we're using consistent learner, that means, okay, you have a zero training error guaranteed, right? Then we claim that if the number of training example is bigger than this guy, then with probability at least 1 minus delta, your learned hypothesis will have true error less than epsilon, right? And we can have a similar statement made for the agnostic learning, right? But here we just list the generalization error bound. If we have M examples, then with probability 1 minus delta, the true error of your learned hypothesis H is bounded by the training error plus this term. So this term is determined by the number of training examples you use, right? It's determined by the confidence level, delta you're choosing. And also it's determined by the VC dimension that reflects or that measures how complex your hypothesis space. Okay. So you can see that the larger the number of training examples, the smaller the right term on the bound, right? That means the smaller, the closer your true error is to the training error, right? And also, the smaller the VC dimension, the smaller this term as well. And the tighter the bound, that means the closer your true error is to the training error. Right. So this result motivates us, right? Motivates us, and the question, right? Can we design some learning algorithm based upon our observation on this bound? So now it gives us hint, right? Why computational learning theory is useful, right? It not only raises interesting theoretical questions, and answering those theoretical questions might also motivate us to develop new learning algorithms. For example, boosting algorithm is motivated by addressing the question that if a concept class is weakly learnable, right? That means there exists a learning algorithm that can produce a classifier that's slightly better than chance. Does this mean the concept class is also strong and learnable, right? That motivates the boosting, right? And now, from the discussion about sample complexity bound and generalization error bound, right? What I'm saying, with some high probability, the true error is upper bounded by training error plus a term with the probability threshold and VC dimension. Right? Can we use this bound to develop a learning algorithm? This motivates the so-called structure risk minimization principle. Right? One well-known and widely used example is called support vector machine. Okay, any questions so far? Okay, great. Now let us jump to our next topic, support vector machine. Support vector machines are a set of very classical and very popular machine learning models, right? It has been like in the research frontier for 20 years or 25 years, right? Before the arising of neural networks or resurgence of neural networks, right? And even although now like support vector machines are no longer the central focus in the machine learning research, because most of the neural researchers is dominated by neural networks, right? It has already been very popular. Right? It has been used in many cases. Right? It is particularly useful for small data and a few hyperparameters, and it can self-adapt. It means that it can adapt pretty well according to the data. Therefore, it has many advantages that neural networks doesn't have. So here I just list a set of examples, use case for the support vector machines, like text and hypertext categorization, facial expression classification, cancer diagnosis and prognosis, bioinformatics, seismic prediction, geology, and so on. Right? So before we dive into the details, right, let us look at the big picture, right, and see so far how many classifiers we have seen, right? How shall we organize them, right? So far, we'll talk about linear models in addition to decision trees, right? We'll talk about linear models, right? Depending on how we're going to evaluate this linear model is good or not, right? We introduce the so-called mistake-driven learning, right? Meaning that, okay, if you make a mistake in predicting some examples, I should update the model parameters to correct mistake, right? So one typical example is called perceptron. This is what you have just look at, right? And also we talk about in theory, how are we gonna view a model is good, right? That brings the so-called pack learning concept and agnostic learning setting, and then brings us the sample complexity bound, the generalization error bound, the structure of the bound, right? And this, as we'll see later, will lead the so-called risk minimization principle with a well-known example support vector machine. And of course, based upon how you're going to define a good learning, what a good learning model is, you can motivate other linear model learning algorithms. For example, the probabilistic learning for linear classifiers like logistic regression, like naive Bayes, all kinds of stuff, right, which we're going to discuss later. Okay, for support vector machines, here we're going to go through. Right? First, we're going to talk about the training principle for support vector machines. You'll see that we're going to choose the so-called margin maximization principle. So previously we have an intuition, right? Explain why intuitively we should pick up linear classifier to have a margin as large as possible. Right? We said, okay, it minimizes the risk of misclassification. Why? Because if you have a larger margin, you kind of like going through the low density regions for both positive and negative examples, right? So reduce the risk, right? We're going to look at that point again, right? And we'll see that actually the margin maximization can be justified by the generalization error bound. We just showing to everyone, right? Then based on this principle, we're going to formulate the support vector machine objective function. By optimizing an objective function, we're going to learn our support vector machine, right? And you will see that the naive formulation is very difficult to optimize. So we're going to do some trick leveraging the insight of linear classifiers. We can convert it into a constraint optimization problem, but it's no longer bi-level optimization problem. It's much easier. Then we can use stochastic gradient descent or stochastic subgradient descent for solving that. Then later, we'll see how can we generalize support vector machines to nonlinear classifiers. That means we have to integrate some trick of feature transformation, which we call kernels. This is our plan. So first, let us talk about how do we pick up a learning principle for linear classifiers. So far, we have known the generalization error bound for the agnostic learning. That is, if I have m examples, right, then we can claim that with probability 1 minus delta, right, at least 1 minus delta, the true error of your hypothesis H is upper bounded by the training error of H on the training set plus this term, right? This term we know that is determined by m, by delta, and also the visit dimension of hypothesis space H, right? As we just discussed, right, the lower visit dimension gives a tighter bound. So imagine that for a different set of machine learning models, right? If they can have the same training error, of course, I'm going to pick up the smaller, the guy who has a smaller visit dimension, because it will make the generalization error bound tighter. That means it will make your generalization error to be close to the training error, right? But now, if we want to train a linear classifier, right, there's a problem. The visit dimension of the whole linear classifier space is already known, it's fixed. It's just the d plus 1. D is the number of features or the input dimension. Okay. Then how can we tighten the bound? Right? There seems no choice. We cannot tighten the bound because you just search over the entire linear classifier space. The visit dimension is there, right? The bound is there. Then how can we improve our linear classifier to tighten the bound, right? So the key idea is as follows. Rather than search over the entire hypothesis space of linear classifiers, right? So you can view like the entire hypothesis space is this giant ellipsis, right? Now, instead of searching over the entire ellipsis, right, I'm just to search over a small subset of linear classifiers. Right? If I can search over the small subset of linear classifier intuitively, I kind of reduce the visit dimension, right? Because the visit dimension for a subset of linear classifiers could be different from the visit dimension for the entire all possible linear classifiers. That's the idea, right? So now let us recall the definition of margin. Right? We see the margin hyperplane for a data set is the distance between the hyperplane and the data points nearest to it, right? So it'll be here, right? For our previous discussion, right? For a linearly separable data set, right? We might have many different choices of linear classifiers. Right? We discussed which classifier shall we choose, right? For H1 and H2. H1 obviously has much larger margin than H2. Right? We discussed and analyzed. We believe that H1 will have better generalization performance. Why? Because H1 is far away from both positive examples and negative examples, right? So by contrast, H2 is much closer. The consequence that if you get closer to the training points, that means you have a chance to go through the high density regions for positive examples and the high density region for negative examples, right? That means on the other side of this decision boundary, you have a high chance to meet examples of the same label, right? Then you have a high chance to make mistakes. That's why using a small margin classifiers is bad, right? If you instead choose a large margin classifier like H1, right, we can believe that these size are low density regions for positive examples, right? So it's unlikely that you will see some positive examples appear on this side to make H1 make a mistake, right? And similarly, H1 also is on the low density region for the negative examples. It's unlikely that you see some negative examples showing up here where H1 is gonna wrongly predict, right? Okay. So now, based upon this intuition, right, let us consider different subset of linear classifiers according to their margin. Okay. Suppose we consider linear classifiers with margins gamma 1 and gamma 2 for the training set. Right? So we define two subsets of linear classifiers, H1 and H2. H1 consists of linear classifiers that have a margin at least gamma 1. H2 is the linear classifiers that have a margin at least gamma 2. So we have gamma 1 is bigger than gamma 2. So that means the linear classifiers in H1 generally have a larger margin than the classifiers in H2. Okay. Then our intuition tells us that the entire set of functions H1 is better. Okay. So can we justify this, right? In theory? The answer is yes. And this is a theorem, right? Theorem provides by that paper. Let H be the set of linear classifiers that separate the training set by a margin at least gamma. Right? Remember, this is the exact definition we just mentioned, right? Then the VC dimension of H is bounded by, upper bounded by this guy. This is 1 plus the minimum between the number of features D and R squared over gamma squared. So remember, gamma here is just the gamma we use to construct H, right? The margin, right? And the R is the radius of the smallest sphere containing data. Remember, in the Mies-de-Bank theorem, R is the maximum length of the input feature vectors, right? So from, by the way, any question regarding the understanding of this, what this theorem says? Yeah, it's just to tell you, okay, if I pick up a particular subset of linear classifiers whose margin is like this gamma, right? Then I can claim that the VC dimension of this H, right, this subset of linear classifiers is upper bounded by this guy. Right? This upper bound is determined by R is something determined by the training set, right? But the gamma is means the margin, right? And now we can see that if we pick a larger margin, because gamma is on the denominator, right? The VC dimension will get lower. And if we get a lower VC dimension from the generalization error bound, you get the better generalization error bound, the tighter bound, right? Because the right term will get smaller. That means your true error will get closer to the training error. Does it make sense? This results actually motivates us, right? When we learn linear classifiers, why do we search over the entire set of possible linear classifiers? We don't need, right? We just need to search the subset of linear classifiers who has the largest margin. Because in that subset of linear classifier, it has the smallest VC dimension. It gives you the tightest generalization error bound, right? That means in the training, we should find the linear classifiers that maximize the margin. That's how we are motivated to develop a new learning algorithm. We're not only fitting the training data, we also want to make sure our linear classifiers has the largest margin, because then it belongs to that particular subset of linear classifiers whose VC dimension is the smallest. Okay. And then it will give me the smallest generalization error bound, right? Given that if your training error is equally small. Right? Okay, that motivates our learning principle. We should maximize the margin. Right? So any questions so far? This is a very, very important first step, explaining why the rationale of doing margin maximization. Because it is not only justified by our intuition, right? It actually justified by our computational learning theory, in particular, the generalization error bound. Again, we're not required to know how this generalization error bound is proved, right? How this VC dimension is derived is not our job. It has already been done by those mathematicians, right? We just need to understand the logic here, right? How it is motivated for us to find a linear classifier with the largest margin, right? Okay, so now with this learning principle in our mind, let us construct SVM objective function, right? But before we do that, right, we should review the geometry of linear classifier. Right? So a linear classifier can be written or can be represented by a hyperplane, right? This hyperplane algebraically is described by an equation, right? That is the classification score is 0, right? And the prediction is made by the sign of the classification score, right? And the distance between any data point and the classification hyperplane is computed as follows, right? It's just the absolute value of the classification score divided by the norm of the weight vector, right? And one very important insight is that we only care about the sign, not the magnitude. So basically, you can arbitrarily skew B, W1, W2, as long as you can still skew them by the same, positive skew, right? It doesn't change the linear classifier at all. geometrically, it doesn't change the position of the boundary at all. Right? Say you multiply all of 3 by 2 by 1000, it gives you the same linear classifier. Right? Now, let us try to construct a learning objective function that maximizes the margin. So according to the definition, margin is the distance of the closest point from the hyperplane. So that means we can write margin as a minimization problem, right? You just minimize. So this guy is definition distance, right? You just go over every point in the training set and take the minimization, solve this minimization problem, you get gamma, right? And meanwhile, because we want to maximize the margin, right? So we need to write down a maximization optimization problem in the outside, right? We maximize the margin in terms of the model parameters, that is W and B, right? Now we can see that we have formulated a bi-level optimization problem, a max-min problem, right? And the numerator here, people usually call it the functional margin. And if you divide the function margin by the weight of W, this is called the geometric margin. Geometric margin is actually the actual distance, right? So, although doing this max-min seems straightforward, right? It just follow an idea maximizing the margin, right? This is quite hard to optimize in practice. This is a max-min problem. And it's bi-level optimization problem. So you can imagine that every time I update WB a little bit, right, I need to reevaluate gamma. That means I have to go through every training point again. Right? And secondly, we can observe that the inner minimization, that is to compute the gamma, essentially is a discrete optimization problem, right? Because you just enumerate example 1, 2, 3, 4, 5 until every example are done, right? You found the closest, the smallest distance, right? And in the author side, WB are continuous, right? So you can see there's a mix of continuous discrete optimization problem. And also the max-min problem, it is a bi-level optimization problem. So it's very hard to solve. Then we want to look at a simplification, right? We don't want to solve a max-min problem. We don't want to mix the continuous and discrete optimization problem. How can we reduce this formulation? I can make it convenient to solve. Okay? We'll talk about that on Thursday. Okay, see you on Thursday.